More than 2 decades ago, we discovered something that changed everything about our place in the universe. Planets exist around other stars, not just our Sun. Since then, we've found more than 5,000 of these distant worlds, and each one tells a different story about how planets are born and die. Some are gas giants bigger than Jupiter, orbiting closer to their stars than Mercury to our Sun. Others are rocky worlds where a year lasts just a few Earth hours. There are planets that orbit two stars at the same time, like in science fiction movies. But what really keeps scientists awake at night is a simple question. If there are so many planets out there, why haven't we found life yet? Are we looking in the wrong places, or is there something special about Earth that we still don't understand? Subscribe to the channel, leave your like and comment from which part of the world you're watching, get comfortable and relax. Let's begin. Did you ever wonder how we first realized that planets exist outside our solar system? The question might seem simple today, but for a long time, it wasn't clear if planets were something unique to our own Sun, or if they orbited stars all across the universe. It was in the mid-1990s when everything shifted. Before that, astronomers had studied the night sky with growing precision, cataloguing stars, galaxies, and other cosmic objects. Still, the direct discovery of a planet orbiting another star had eluded us. People sometimes speculated about the existence of other worlds, but there was no concrete proof. It was a fundamental mystery that sparked curiosity among both experts and the public. The answer finally came in 1995, marking a major turning point in our understanding of the cosmos. The discovery unfolded when a pair of Swiss astronomers, Michel Mayor and Didier Queloz, noticed subtle changes in the light coming from a sun-like star called 51 Pegasi, located about 50 light-years away from Earth. They weren't seeing a planet directly, of course. Instead, they detected a repeating pattern, a wobble in the star's motion. This wobble was a telltale sign that something with significant mass was pulling at the star as it moved around in space. After careful analysis, they announced that a planet, roughly half the size of Jupiter, was orbiting 51 Pegasi. The scientific community quickly realized this was not just a singular fluke. It was evidence that planets could form around other stars, and it opened the door to the search for many more. This first confirmed exoplanet, known as 51 Pegasi b, looked nothing like anything in our own solar system. It was a gas giant orbiting extremely close to its parent star, so close that its year lasted just over 4 days. That was a big surprise, because astronomers had always thought big gas giants could only form farther out from a star, as happens with Jupiter and Saturn in our own system. The discovery challenged all existing theories about how planets form and where they might appear. As scientists looked back at the data, they realized they might have missed similar signals in past observations simply because they hadn't expected planets to behave this way. The lesson was clear. Assumptions had limited what people thought was possible. Now the sky was wide open for reimagining the universe. After that initial breakthrough, the search for exoplanets gained tremendous momentum. Astronomers began to refine their observation techniques, developing more sensitive instruments and smarter ways to look for the subtle clues a planet leaves on its parent star. Each new detection method added a different piece to the puzzle, making it easier to find more. Over the years, the discoveries came faster and covered a wider variety of planets. Some were hot gas giants like 51 Pegasi b, others were rocky, more Earth-like worlds orbiting smaller, cooler stars. There were planets with wildly elongated orbits and even systems with several planets orbiting a single star, sometimes in very tight configurations. The more astronomers looked, the more it seemed that planetary systems could come in just about every form imaginable. What makes these discoveries especially significant is not just the numbers. Every single new exoplanet tells us something about the rules of physics and chemistry in different environments. For instance, the fact that gas giants can exist close to their stars suggests that planetary systems can change in dramatic ways after they form. Planets can migrate, environment can shift, and new types of worlds can emerge. With each newly discovered planet, astronomers have learned to be cautious about making broad generalizations. Nature keeps finding ways to surprise us. The diverse catalogue of exoplanets keeps growing, and with over 5,000 confirmed by the year 2024, it's clear that planets are a common outcome of star formation. This is a huge leap from the old idea that our solar system might be unique. before exoplanets were detected and confirmed, most people, including scientists, assumed that planetary systems would look a lot like our own. The Sun at the center, with a set of rocky planets inside, a few gas giants farther out, and perhaps some small, icy bodies at the edge. As exoplanet discoveries poured in, that tidy image fell apart. Some systems have gas giants closer in than Mercury is to our Sun, while others have tightly packed sets of rocky worlds with different compositions. There are planets orbiting binary stars where the gravitational tug-of-war creates entirely new types of orbital behavior. Some exoplanets even seem to have formed in strange environments like the remains of dead stars or inside clouds of dust kicked out by supernovas. Planetary systems now look as varied as the stars themselves. Confirming the existence of exoplanets was also a huge motivation for building better telescopes and developing more sophisticated methods for analyzing data. The Kepler Space Telescope, launched in 2009, took the search to a whole new level by continuously monitoring more than 150,000 stars for several years. By looking for tiny dips in a star's brightness when a planet passed in front of it, Kepler was able to discover thousands of candidate planets, including many similar in size to Earth. Data from Kepler revealed that planets come in a huge diversity of types and sizes, and that planets about the size of Earth might be especially common around small, cool stars called red dwarfs. This was a game changer because it suggested there could be millions or even billions of potentially habitable worlds just in our own galaxy. Technology did not stop advancing with Kepler. Next came the Transiting Exoplanet Survey satellite, launched in 2018, which set out to search the brightest stars near Earth for more planets, and the James Webb Space Telescope, which started operating in 2022 and can measure atmospheric details of exoplanets with never-before-seen precision. With every passing year, our eyes on the universe have become sharper, and the catalogue of exoplanets keeps growing. What was once a rare event, discovering a new planet, has now become an almost routine part of modern astronomy thanks to these technological leaps. Each exoplanet discovered adds a little context to some of the biggest questions humans have ever asked. Are we alone in the universe? Is our world rare or is it typical? Is life an inevitable outcome once you have the right ingredients? Or is it something that happens only under the most specific conditions? The sheer number of exoplanets already discovered helps fuel these questions. It's now clear that most stars in the Milky Way, maybe even all of them, have planets. That realization fundamentally changes the way we think about life elsewhere. It shifts the search from "are there other planets?" to "which of these worlds might be like ours, and how do we find them?" Part of what makes this all so fascinating is that each new discovery not only answers questions but also raises brand new ones. For example, why do so many systems have huge planets right next to their stars, when ours doesn't? Do rocky planets like Earth tend to form more often around certain types of stars? Is there something especially unusual, or maybe just random, about the arrangement of planets in our solar system? Even more intriguing, what kinds of atmospheres, climates, and even potential forms of life might exist on all these different worlds? The study of exoplanets has become one of the most dynamic fields in all of science because with each new discovery, the universe gets a little bit bigger and the possibilities expand. It's worth pausing for a moment to think about how these discoveries have changed the way we see our place in the cosmos. For centuries, people assumed Earth was at the center of everything, with other planets orbiting our sun and stars as little more than distant pinpricks. The discovery of exoplanets shifted that perspective. Instead of a universe focused on us, we see one that's full of worlds we've just started to discover. The stars we see with the naked eye when we look up at night form just a tiny fraction of the planetary systems that exist. Our own sun and its family of planets are just one example in a galaxy that's probably brimming with hundreds of billions of planets. The excitement around exoplanet research doesn't just come from the numbers, but also from the stories behind individual discoveries. Every so often, scientists find a planet that stands out, a planet located inside its star's habitable zone, perhaps, or one with signs of water vapor in its atmosphere. These planets grab worldwide attention, stirring the imagination about what it might be like to walk on their surfaces or look up at their alien skies. Some of these worlds orbit stars similar to our own, while others circle around dim red dwarfs or even burn inside double-star systems. The discoveries are so compelling that they have inspired new generations of scientists, engineers, and curious minds to turn their attention to the universe beyond our own solar system. One key aspect of exoplanet research is how it encourages collaboration across traditional boundaries. Astronomers work together with physicists, chemists, computer scientists, and even amateur stargazers to interpret data and sift through the vast amounts of information gathered by telescopes on the ground and in space. Machine learning and artificial intelligence help analyze patterns that might otherwise go unnoticed. International teams build observatories and share resources in the hunt for new planets. As a result, exoplanet science is a truly global effort, bringing people together in the quest for knowledge about the universe. It's a shining example of how scientific curiosity can unite people from all corners of the world. As the field has grown, the meaning and significance of each discovery have also deepened. In the early days, just confirming one planet outside our solar system was amazing. Now, scientists are able to study entire planetary systems, comparing how planets interact with each other and their stars, and examining how unique or common Earth-like conditions might be. They are beginning to detect and measure atmospheres on distant worlds, looking for clues about their chemistry, weather patterns, or even potential signs of life. The search is always evolving, often moving faster than anyone expected. What once was considered science fiction is now a regular part of everyday astronomy. One impressive feature of exoplanet discovery is how it has upended old views on the formation of planets and the organization of entire star systems. The assumption that our solar system represented a typical model has been shattered by the bizarre and unexpected arrangements found elsewhere. Some systems feature massive gas giants packed in close to their host star, while others display rocky planets subject to wild temperature swings. There are even exoplanets that orbit in the opposite direction of their star's rotation, a phenomenon that up until recently was thought almost impossible. The more we study these strange worlds, the clearer it becomes that the universe's creativity knows no bounds. Perhaps the greatest takeaway is how much more remains to be discovered. As telescopes become more powerful and observation techniques become more refined, the number of known exoplanets is sure to continue growing. With every new planet, a piece of the giant cosmic puzzle falls into place, but the big picture still evolves. The study of exoplanets has become one of the central journeys in modern astronomy, continually pushing us to rethink assumptions, build better technology, and stretch our imaginations. Each step forward opens up 10 new questions, making the science feel fresh and exciting year after year. Sometimes the significance of exoplanets as a field spills out into other areas of science and even into culture and the arts. Writers and filmmakers draw inspiration from the real-life discoveries of new worlds, while teachers use the latest exoplanet findings to ignite curiosity in their students. The field has changed how people talk about our planet, reminding us that Earth is just one small world among countless others. It has become a symbol of the endless possibilities that still exist for exploration and discovery. In this way, exoplanet research is not just about numbers and statistics, but about transforming the way humans see themselves in the universe. Even after all this time, one of the most exciting things about exoplanet discovery is that anyone, anywhere, can look up at the night sky and know that some of those stars might have worlds orbiting around them. These discoveries show that the universe is teeming with planets, with new worlds waiting to be found in every direction you look. It's a realization that encourages both curiosity and wonder, and it's one that's likely to inspire people for generations to come. So, the discovery and significance of exoplanets isn't just about finding planets in other solar systems. It represents one of the greatest leaps in our understanding of how common planets actually are, how varied and fascinating their systems can be, and how much we still have to learn. It pushes every boundary in astronomy, offers new chances for the search for life, and shows that our place in the cosmos is both ordinary and extraordinary at the same time. With each world discovered, our sense of the universe grows, and the possibilities for understanding it deepen. Whether you're an astronomer studying the data or someone catching up with the latest discoveries on the news, it's a story that continues to unfold, full of surprises, new questions, and the thrill of what might come next. How in the world do scientists find planets orbiting distant stars when we can't even see those planets directly? It sounds almost impossible, but astronomers have become pretty ingenious at spotting worlds far outside our solar system using a range of detection methods. Each approach takes advantage of different effects that an unseen planet can have on its host star or the light coming from it. These techniques have evolved over the years, moving from methods that first worked only for massive planets around bright nearby stars to strategies that now allow us to find much smaller and much more distant worlds. The story of how exoplanets are detected is full of clever ideas, trial and error, and a lot of refinement over time. Probably the most well-known method for discovering exoplanets is called the transit method. Here's how it works. Whenever a planet passes directly in front of its star as seen from our point of view, it blocks a portion of the starlight. That causes the brightness of the star to dip ever so slightly for a short period of time. The dip is tiny, often less than 1%, and it lasts only as long as the planet is crossing the face of its star. For something as big as Jupiter, you might get a dip of about 1%, but for an Earth-sized planet orbiting a Sun-like star, the dip could be only a fraction of a percent. These small drops are invisible to the naked eye, and even to most telescopes, but can be picked up by highly sensitive instruments attached to ground-based telescopes or by specialized satellites in space. The Kepler Space Telescope used this method to spectacular effect, watching more than 150,000 stars at once and capturing thousands of planetary candidates by recognizing the recurring pattern of their transit dips. A key advantage of the transit method is that it can be done in bulk, searching many stars at a time and yielding large numbers of planet candidates. This is how we've uncovered all sorts of planets, including some similar in size to Earth, and some that lie in the so-called habitable zone of their stars where liquid water could exist. The technique is especially efficient for finding planets that are close to their host stars because those planets orbit more often, and that means their transits repeat more often too. On the other hand, this method does have its limits. You won't catch a transit unless the orbit of the planet lines up just right with our line of sight. In real terms, that means you're only seeing a fraction of the planets that actually exist, the ones whose orbits just happen to be edge-on from where we're observing. Another important technique is the radial velocity method, sometimes also called the wobble method. Instead of waiting for a planet to pass in front of its star, astronomers look for signs that the star itself is moving ever so slightly back and forth in space, tugged by the gravity of an orbiting planet. Even a massive planet will only nudge its star a little, but with sensitive enough instruments, those movements show up as shifts in the spectrum of light coming from the star. This is similar to the Doppler effect you notice when you hear an ambulance siren change pitch as it goes past you. If the star is moving toward us, the light is shifted a bit to the blue side. If it's moving away, the light gets shifted to the red. By measuring how the spectrum changes over time, scientists can tell if a planet is causing the star to wobble, and from the amount of wobble, they can estimate the planet's mass and how far it is from its star. The radial velocity method was responsible for the discovery of the first confirmed exoplanet around a Sun-like star in 1995. It is particularly useful for detecting big planets, the kind that have a strong gravitational pull and cause a noticeable effect on their stars. As instruments have grown more precise, astronomers have managed to find smaller and lighter planets with this method as well. One challenge is that stars themselves can be noisy. Their surfaces can swirl and tremble in ways that can sometimes look like a wobble from a planet. Careful calibration and new data analysis methods have helped reduce these errors, and in combination with other methods like transits, they can confirm the presence of planets. A different approach comes with direct imaging, which is exactly what it sounds like. Taking a picture of an exoplanet itself. This method might seem the most straightforward, but it's actually very difficult. The main problem is that stars are much brighter than any planets orbiting them. Imagine trying to spot a tiny dim lamp next to a giant spotlight. The light from the star completely drowns out the planet in almost every wavelength. To get around this, astronomers use special instruments called coronagraphs or star shades, designed to block the starlight and let the dimmer planet become visible. They also use long-exposure photography, adaptive optics that tweak the mirror of the telescope many times per second, and other tricks to tease out that faint bit of light. Direct imaging works best for planets that are relatively young and hot, glowing in the infrared, and orbiting far away from their stars, where there's more space between the planet and its star in the sky. So far, only a few dozen exoplanets have been confirmed this way, but the technique gives us a chance to study those planets in detail, even getting rough images and spectra to learn about their atmospheres. Gravitational microlensing uses a completely different property of nature, gravity's tendency to bend the path of light. When a massive object like a star passes between us and a distant background star, the gravity of the foreground star can act as a lens to magnify and brighten the light of the background star. If the foreground star has a planet orbiting it, for a short time, the brightness curve of the event will get an extra boost as the planet's gravity bends even more light toward us. Astronomers look for these sudden brightening events using wide-field surveys that watch hundreds of millions of stars at a time. Microlensing can discover planets that are far from their host stars or in regions of the galaxy where other methods would struggle. The catch with microlensing is that it relies on chance alignments. You don't know when or where an event will happen, and the events are usually once-in-a-lifetime occurrences for any given star system. Still, this approach has proven valuable for detecting planets that would otherwise go unnoticed, including some so-called rogue planets that don't seem to orbit any star at all. Astrometry offers yet another way to spot exoplanets. This technique is all about extremely precise measurements of a star's position in the sky. If a planet is tugging on its star, it makes the star trace out a very small loop or wobble as it moves through space. Detecting these motions requires measuring positions with micro-arc-second precision, which is beyond what regular telescopes can manage from the ground because of atmospheric turbulence. Space telescopes, like the European Gaia mission, are changing the game by enabling measurements fine enough to pick up these movements for thousands of stars. Astrometry complements radial velocity and transit methods by picking up signals from planets in wider orbits, especially ones that don't pass in front of their stars from our vantage point. Historically, astrometry has been slow to deliver planet discoveries, but advances in technology are making it more productive over time. These main methods often work even better when paired together. For example, when a planet is found both by its transit and by detecting the radial velocity wobble of its star, astronomers can learn much more about it. The transit provides the planet's size, while radial velocity adds information about the planet's mass. Put together, these measurements help reveal the planet's density, letting scientists figure out whether it's likely to be rocky like Earth or a ball of gas and ice like Jupiter or Neptune. Over the years, this kind of combined approach has brought us some of the most detailed portraits of alien worlds. What happens behind the scenes is just as interesting as the big discoveries themselves. To do any of this work, astronomers need very precise instruments and a good understanding of how stars behave. They have to weed out false detections caused by sunspots, stellar flares, or instrumental errors. Space telescopes offer advantages because they're above the blurring effects of Earth's atmosphere, but ground-based telescopes have the benefit of being bigger, easier to upgrade, and less expensive to operate. The choice of method and telescope depends on what kind of planets scientists are hoping to find and what stars they want to study. In recent years, citizen scientists and machine learning have also started to play big roles. Volunteers around the world can help sift through the mountains of data produced by surveys like Kepler and TESS, marking possible signals that a computer might miss. Algorithms help spot subtle, repeating patterns that could belong to planets, flagging these for follow-up analysis by astronomers. This has made the process of confirming new exoplanets faster and more reliable, turning what was once painstaking, manual work into something that moves at a much quicker pace. Different methods bring their own set of biases and strengths. The transit method finds many planets close to their stars, so it tells us a lot about hot Jupiters, big gassy planets in tight orbits, but it misses some in wider orbits that rarely transit. Radial velocity can pick up planets further out, but it favors bigger and heavier planets and can struggle with smaller, distant worlds. Gravitational microlensing is good for finding planets far from any star, including those that float through the galaxy alone, but the events are rare and unpredictable. Astrometry excels at picking up wobbles from planets with long orbits, potentially even analogues to Jupiter or Saturn in other star systems. Direct imaging is the only way to actually see a planet, but so far it works best for massive young planets at large separations. As instrument technology improves, so does our ability to spot smaller planets, like those similar to Earth. For instance, the latest spectrographs can measure shifts in starlight with astonishing precision, down to just a few centimeters per second, which makes it possible to detect Earth-mass planets orbiting sun-like stars. Future missions are aiming even higher, trying to identify rocky planets in the habitable zones of nearby stars and analyze their atmospheres in detail. Another fascinating aspect of these techniques is their ability to tell us things about the planets beyond just their presence. The way a planet dims its star during transit can reveal clues about its atmosphere. Certain wavelengths of starlight are absorbed by different elements and molecules, so by studying the starlight before, during, and after a transit, scientists can infer if the planet's atmosphere contains things like water vapor, methane, or even oxygen. In addition, the precise timing of transits or wobbles can indicate if other planets are present in the system, tugging gravitationally on the one being measured. This can uncover entire planetary systems and give us a sense of how crowded or spread out different solar systems can be. The discoveries made using these detection methods have upended our understanding of what's possible for planetary systems. Planets come in all sizes, densities, and arrangements, and a big reason we know that is because different techniques catch different types of planets. For example, hot Jupiters were spotted early because they are big and close in, so they produce strong signals in transit and radial velocity data. But now, with new technology, smaller planets called super-Earths and mini-Neptunes are turning up by the hundreds. Gravitational microlensing has revealed unexpected populations of wandering planets, and direct imaging has given us glimpses of chaotic, still-forming systems around young stars. There are loads of upgrades and new missions on the horizon meant to sharpen our detection tools even more. The James Webb Space Telescope can look for the minute temperature differences and subtle chemical fingerprints in exoplanet atmospheres, adding a whole new layer to what we can learn from transits and direct imaging. The European Space Agency's Gaia mission keeps improving our ability to use astrometry to spot new wobbles in star positions. Dedicated ground-based observatories are being fitted with cutting-edge adaptive optics and ever better spectrographs. All these developments will continue to add depth and detail to our growing family of known exoplanets. Another area of progress is in reducing false positives. Sometimes, phenomena unrelated to planets can mimic the signals astronomers are looking for. For example, binary stars that eclipse each other can create dips in brightness, similar to what we see in planet transits. Starspot activity or magnetic flares can look like radial velocity wobbles. Confirming new planets often involves multiple teams using several methods to cross-check their findings, ruling out other astrophysical explanations. This careful vetting means the exoplanet catalogue grows steadily more reliable over time. It's interesting to see how these methods drive the questions that scientists can ask. Early on, the focus was just on confirmation. Find an exoplanet and make sure it's real. Now, the bar is higher. Astronomers want to know if the planet is rocky, if it has an atmosphere, if that atmosphere contains water or oxygen, what the climate might be like, and how the planet formed in the first place. The discovery process has evolved from just spotting planets to building an entire picture of what those planets are like and how their solar systems work. All these advancements rest on a mix of clever physics, sophisticated software, and increasingly precise hardware. Scientists keep inventing new ways to pull weak signals out of noisy data and combining observations from different methods to learn as much as possible. Ground and space-based telescopes feed each other's discoveries. If TESS spots a likely transit in a nearby star, ground-based observatories might follow up to get a better look. If Gaia finds a likely astrometric wobble, teams can go back to older data, looking for a transit or a radial velocity confirmation. Collaboration, cross-checking, and using many different approaches is now just the standard way things get done. The sheer quantity of data is another challenge. Each survey mission generates literally terabytes of information, far too much for any one person or even a small group to go through by hand. This is why automated pipelines, machine learning, and public participation through online platforms have become so critical. They let scientists keep pace with the flood of information and make sure no interesting signal slips through the cracks. As the field moves forward, new ideas keep popping up for how to find planets under even trickier circumstances. For example, some astronomers are experimenting with time domain astronomy, watching stars for years to study variations that could signal planets with very long orbits. Others are planning large interferometers, where multiple telescopes work together to simulate a much larger instrument, which could eventually allow the direct imaging of smaller, Earth-sized exoplanets. Breakthroughs in high-contrast imaging techniques could let us photograph planets much closer to their stars than ever before. With each new generation of technology, our eyes on the universe become a bit sharper. The pace of discovery has only picked up, and the catalogue of known exoplanets is growing faster now than at any other time in history. There's a sense within the field that even more excitement is just around the corner. Thinking about how far we've come in such a short time is pretty striking. In the 1990s, only a handful of planet candidates had been suspected, and their reality was hotly debated. Now, there are well over 5,000 confirmed exoplanets and thousands more candidates awaiting confirmation, all made possible by constant improvements in our methods and technology. The story of finding exoplanets is really about expanding horizons, both literally and figuratively. Each detection method brings its own piece of the exoplanet puzzle, and when scientists put them all together, the universe looks far richer and more complex than anyone imagined a few decades ago. What started as a search for a few distant hidden worlds has become one of the main frontiers of modern astronomy, opening up billions of potential new places to investigate and understand. With every planet discovered, the range of possible answers to the question, "What's out there?" just keeps growing, and the techniques for finding those answers keep getting sharper. The process is still ongoing, and with new tools on the way, it's a safe bet that we'll keep uncovering new secrets about worlds far beyond our own. All of these new observation methods have made it possible not just to find more planets, but to appreciate how wildly different they can be. As scientists have expanded the catalogue of exoplanets, one thing has become incredibly obvious. The kinds of planets and orbits we see out there aren't anything like the neat, predictable solar system most people learned about in school. For so long, our 8 planets provided the standard template. We knew about rocky planets like Mercury, Venus, Earth, and Mars close into the Sun, then gas giants, then icy bodies farther out. But with all this new exoplanet data piling up, astronomers quickly noticed that the universe is way more creative than our solar system suggests. Take the so-called hot Jupiters, for example. These are giant gas planets, similar in size or even bigger than our Jupiter, but they orbit their stars very closely. Some take only a few days to complete a single orbit, which means their year could be over in less than 1 Earth week. They are blisteringly hot on the side facing their star and usually have very short seasons as a result of how tight and circular those orbits are. What stuns most scientists is that in our own solar system, the gas giants are far from the Sun, where things are cooler and ices can form. The existence of hot Jupiters turned theory on its head, making researchers realize that planets probably form and migrate in ways not previously imagined. Their atmospheres, baked by intense starlight, can have clouds of vaporized metals and temperatures of thousands of degrees Celsius, making them completely different from anything nearby. Besides these giants sitting right next to their stars, there are super-Earths and mini-Neptunes, which occupy a middle ground in size between Earth and Neptune. These types of planets are among the most common discoveries in exoplanet surveys, yet we do not have anything quite like them in our own solar system. Super-Earths range in mass from about 2 to 10 times that of Earth, while mini-Neptunes are a bit bigger and often have thick gaseous envelopes. The surface conditions on these planets could vary from hot and steamy to icy, or even rocky with oceans. Some may have atmospheres rich in hydrogen and helium, while others might support thick clouds or layers of water vapor. It is not clear yet whether super-Earths are more like oversized rocky planets or gas dwarfs with a rocky core. Mini-Neptunes continue to puzzle scientists with their low densities and puffy atmospheres. When it comes to orbits, the variety is just as dramatic. While our solar system's planets mostly orbit in flat, nearly circular paths around the Sun, many exoplanets follow much more elliptical orbits, like stretched-out ovals that bring them alternately very close and then far away from their star during each revolution. These kinds of orbits can lead to wild swings in temperature and seasons, totally unlike anything we see on Earth or Mars. Some planets orbit on tilted planes, while others have orbits that are even inclined at dramatic angles compared to the disk of their solar system. This suggests that collisions or close gravitational encounters have played a big role in how these systems ended up the way they are. In a surprising twist, some star systems are far busier than our own. Astronomers have found exoplanet systems with more than half a dozen planets packed into orbits so close together that they would all fit inside the orbit of Mercury. In these cases, planets can interact and tug on each other, creating complex orbital dances. Other systems are the opposite, with only one big solitary planet orbiting a star, or even planets found floating alone in interstellar space, apparently ejected from their original systems. These wandering or rogue planets are a whole new category and challenge our ideas about what a planetary system even is. Another strange case is the discovery of planets circling not one, but two stars. These circumbinary planets travel around a pair of suns, and their orbits can be stable for long periods as long as the system is balanced just right. Watching these systems in action, scientists can observe naturally occurring three-body dynamics, a complicated gravitational puzzle that adds a layer of richness to how planetary systems work. Findings like these have inspired new questions about whether planetary systems in binary or even trinary star environments can form and persist, and whether such planets could ever support life. Some of the most extreme types of exoplanets have gained nicknames like lava worlds or diamond planets based on their characteristics. For example, some rocky planets orbit so close to their stars that their surfaces are likely covered in lakes of molten lava. Others orbit stars rich in carbon, and scientists have suggested that under the right conditions, a planet's interior could crystallize into diamond. These kinds of discoveries show just how widely the conditions for planet formation can vary, depending on everything from chemical makeup to how turbulent the region around a young star might be. Atmospheres are another dimension where diversity rules. Some exoplanets are so close to their stars that their atmospheres are being blasted away by high-energy radiation, creating tails like comets. Others retain thick, cloudy blankets of chemicals that can obscure even the outline of the planet below. Astronomers have detected atmospheres dominated by water vapor, methane, carbon monoxide, or even exotic compounds like titanium oxide. The ingredients depend on how much energy the planet receives, what elements were present during formation, and whether volcanic activity or other processes are delivering material from the interior up to the atmosphere. The distances between planets and their stars can be tiny or enormous. Some planets live so close that they are practically touching their stars, while others are dozens of times farther away than Pluto is from our Sun. Some stars, in turn, have planets at every imaginable interval, clustered tightly together or scattered across wide, empty expanses. The arrangement of these orbits often depends on the history of gravitational shuffling in each star system, shaped by past migrations, collisions, and even close encounters with other stars. There is growing evidence for planets with extreme tilts, rotations, or unusual day lengths. A few exoplanets rotate so slowly that a day there can stretch on for weeks or months, while others are tidally locked, meaning one side always faces the star and the other is in permanent night. On tidally locked planets, there might be dramatic differences between blistering heat on the day side and deep cold on the night side. Some worlds spin so rapidly that their shape is distorted, bulging at the equator more than Earth ever does. When astronomers get enough data from observing multiple transits or from a direct image, they can sometimes piece together these rotation rates and even map out storm systems, jet streams, or giant hurricanes bigger than anything seen on Jupiter. The diversity of orbits goes even deeper. Multi-planet systems give us some of the best looks at how complex these arrangements can be. In some cases, the timing of a planet's transit will shift slightly back and forth, suggesting gravitational tugs from nearby planets in resonance. Resonances are situations where the positions of two or more planets line up regularly, and their repeated gravitational pull helps lock the system into a stable pattern. The TRAPPIST-1 system, for example, has 7 Earth-sized planets in tight, resonant orbits, and each planet's year is tied to the periods of its neighbours. This leads to a complicated but long-lived clockwork dance where each orbit is nudged by the rest, but the system remains stable for billions of years. Among all this variety, astronomers also find planets with highly unusual compositions. Ice giants with thick methane clouds, rocky super-Earths coated in mineral dust, planets with iron rain, or clouds of silicate glass. These are just a few of the atmospheric and surface conditions being theorized, and in some cases directly detected. What the telescopes pick up is often just a faint signal, needing lots of careful analysis to figure out what is really there. Sometimes planets in similar orbits around similar stars turn out to have wildly different makeups, showing that there is no simple recipe for planet building that fits all cases. There is also compelling evidence that the chemical fingerprint of a star can influence the types of planets it hosts. Stars that started with high metallicity, that is, more elements heavier than hydrogen and helium, often have a greater chance of hosting gas giants. Other stars, rich in certain types of carbon or oxygen, might help form planets with different surface conditions. The diversity arises from the way dust and gas clump together in the disk around a young star, how quickly the star forms, and what other material or stars happen to be nearby. The more systems scientists investigate, the more they realize that planet formation is a messy, churning process. Planets can start in one location and then move, either slowly over millions of years, or suddenly because of a close encounter. Some planets might be swallowed up by their star, flung out into deep space, or fused together by violent collisions. These processes leave behind systems that can look organized or chaotic, with arrangements nothing like our own. Some even suggest that our familiar solar system, with its stable, nearly circular orbits, could be on the rare, quiet side of the spectrum. Besides the planets themselves, astronomers have begun to find strong evidence for moons and planetary rings in some systems. Giant exomoons, moons orbiting exoplanets, could be common but are still tricky to confirm with today's instruments. Rings might show up as odd features in the dips of starlight during a transit, or as strange patterns in the dust near young stars. The possibility of Saturn-like ring systems or Jupiter-like moon swarms existing around planets in other solar systems adds even more richness to the diversity of planetary setups that are possible. Even the way planets reflect and emit light adds to how different they appear. Some worlds are among the darkest objects ever measured, reflecting less light than charcoal, while others shine brightly or even glow with their own heat. Younger, massive planets may still be hot from their formation and visible in the infrared, while older, smaller ones gradually cool, losing their detectable signatures unless they pass in front of their stars. The broad takeaway from all this is just how inventive nature seems to be when it comes to shaping planets and their paths around stars. Every new planet found seems to test the boundaries of what astronomers thought was possible. From burnt-out cinders orbiting dead stars to huge, puffy giants circling at the edge of a solar system to tightly packed chains of rocky planets orbiting dim red dwarfs, there is no single recipe for a planetary system. And as the catalogue of known exoplanets climbs past 5,000, each new addition challenges scientists to rethink old models. Astronomers now study how planets interact inside those strange new systems, how atmospheres survive or get stripped away, how different forms of weather might arise, and even whether some of these worlds could support life. The more they look, the more options they discover, including the possibility of habitable zones that are wider or narrower than previously supposed, or environments once considered hostile, now reimagined as possibly promising. Many researchers are also turning their attention toward planetary migration. It is becoming clear that many planets didn't form where we currently find them. They may have started farther out and then drifted inward, or they may have been nudged by the gravity of other planets or passing stars. These migrations help explain why hot Jupiters exist, why some systems are so crowded, and why others ended up with lone, distant planets. Detailed simulations and observations are helping build a picture of solar system evolution that is a lot more dynamic and disorderly than the textbook image of planets forming and staying put. Surveys are pushing into new territory with each new telescope launch or upgrade. The James Webb Space Telescope is already allowing astronomers to look at the light from exoplanet atmospheres in detail, finding signatures of water vapor, carbon dioxide, and other molecules. The more data collected, the more we see previously unknown combinations of planet sizes, densities, and orbital arrangements. Projects like TESS and Gaia are scanning ever larger patches of sky, making it likely that the weirdest and most interesting planetary types are still waiting to be discovered. Astronomers also examine the age of planetary systems to see how stability and chaos might arise over time. Young systems, only tens or hundreds of millions of years old, are often messier, with debris disks, leftover gas, and changing orbital patterns. As systems age, they may settle or be shaped by events like supernovae or nearby stellar flybys. Some planets might experience billions of years of slow change, quietly adjusting their orbits, losing or gaining moons, or swapping places with neighbors. The effects of time, composition, and chance all weave together to make each system unique. The search for habitability adds one more layer of interest. Some exoplanets orbit inside their star's habitable zone, where temperatures could allow liquid water to exist on the surface. But as we have seen, composition, atmosphere, orbit, and even the presence or absence of a moon or strong magnetic field will all matter too. Each possible combination points to a staggering array of environments, some familiar, others completely beyond current experience. This stunning diversity does not just broaden our understanding of what a planet can be. It has a direct impact on how we search for life, how we define habitability, and even how we think about the origins of our own solar system. By cataloguing the shapes, sizes, orbits, and atmospheres of exoplanets, astronomers are piecing together the rules, if there are any, that decide what kinds of planets form, where they migrate, and how they evolve. Every discovery pushes new questions. Could there be planets made mostly of exotic ices or rocky worlds with surface volcanoes spewing iron or glass? Might some systems hold lost, ancient planets ejected long ago? And can we predict with any certainty which kinds of exoplanets might be the most common in the galaxy? Or are we destined to keep finding new surprises? No matter the answers, what is clear so far is that the universe's approach to planet building is almost boundless in variety. With more advanced telescopes bringing in greater volumes of information, scientists expect to keep running into new types of celestial architectures. The lessons learned keep helping to update planetary formation models and feed the ongoing search for life beyond Earth. All of it drives home just how remarkable and surprising the universe can be, with planets and systems that stretch the imagination and challenge everything we thought we knew about what it means to be a planet. All this variety pushes scientists not just to catalogue exoplanets, but to figure out which of them might actually be good places for life as we know it. One of the biggest ideas guiding that search is called the habitable zone. This is the range around a star where temperatures are just right for liquid water to exist on the surface of a planet, assuming it also has a suitable atmosphere. People often call this area the Goldilocks zone because it is not too hot and not too cold, but just right for water to be in its liquid form. The spot where a habitable zone falls depends a lot on the type and size of the star. Hotter, bigger stars have their habitable zones farther out, while cooler, smaller stars require a planet to snuggle up much closer in order to stay warm enough for water to be liquid. That means that for each type of star, the planets that fall inside the habitable zone can vary a lot in distance and possible climate. The actual definition of a habitable zone has to take into account more than just distance. You also have to think about a planet's atmosphere. If a planet has a thick blanket of greenhouse gases like carbon dioxide, it can trap more heat and stay warmer, even if it's a bit farther out from the star. If it has little or no atmosphere, or mostly reflects sunlight, it'll probably freeze, even if it is technically sitting in the right spot. Venus, for example, is within the Sun's habitable zone, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect, making it far too hot for life. Mars is also inside the outer edge, but with barely any atmosphere, it is cold and dry most of the time. The lesson is, there's a lot more going on than simply figuring out the distance from the star. Now, when it comes to exoplanets, scientists look for those that orbit within their star's habitable zones as prime places to search for life. Missions like Kepler and TESS have found several dozen planets that at least meet this basic requirement, and more candidates show up every year. Some of these so-called potentially habitable planets are similar in size to Earth, or only a bit heavier, which also helps when thinking about gravity and the likelihood of holding on to an atmosphere over billions of years. The size and composition of the star are really important too, because smaller, cooler stars called red dwarfs have their habitable zones extremely close in. That brings up its its own set of challenges, since those stars tend to flare up with high-energy bursts much more often, and any close-in planet gets hit by a lot of radiation. Even for planets in what looks like the perfect spot in the habitable zone, scientists have to be careful about jumping to conclusions. There are so many factors that can throw off conditions for life. Everything from whether a planet is tidally locked, so one side is always scorched and the other frozen, to how much of a magnetic field it has. A strong magnetic field, like Earth's, helps protect an atmosphere from being blown away by solar radiation. If a planet has little or no magnetic field, it could lose its air over a few million years, making it tough for water to stick around. Astrobiologists, the folks who study the possibilities for life elsewhere, spend a lot of time thinking about this kind of detail. Habitability depends not just on temperature and water, but also on the chemical makeup of the planet and its surroundings. For a long time, people assumed life anywhere else would need the same ingredients as on Earth: carbon, water, a bit of nitrogen, and so on. As more exoplanets have been discovered, scientists started to wonder if it might be possible for life to develop in different environments. Could life use ammonia instead of water, for example? Could silicon-based life exist, given the right energy sources and chemistry? These questions remain open, but for now, a lot of research is still aimed at finding worlds most similar to Earth, since those are the easiest to imagine life taking hold. The search for signs of life, called biosignatures, involves a lot of careful work. Scientists look for certain molecules in a planet's atmosphere that seem hard to produce without living things. Oxygen is a big one. On Earth, most of our oxygen is made by plants and tiny ocean organisms. Methane can also be a good sign, since much of the methane in Earth's atmosphere gets released by microbes, though it can also be made by volcanoes and other geology. A really strong clue would be finding both a lot of oxygen and methane together in an atmosphere, because they tend to react and destroy each other if there isn't a source continually producing them. Finding such a combination far from Earth would be extremely interesting. Actually spotting those molecules is no small feat. Planets are tiny and dim compared to their stars. Detecting a faint signature of just a few molecules takes incredibly precise equipment and a good understanding of how light passes through an atmosphere. The James Webb Space Telescope, which started its science operations in 2022, has already started capturing atmospheric data from a handful of exoplanets by looking at how starlight gets filtered as a planet crosses in front of its star. For star systems closer to us, astronomers are developing new tools that might be able to spot even smaller biosignature signals in the next few decades. Even with advanced technology, there's always the possibility of false alarms. Methane, for example, can exist on a planet without any life at all, since certain geological processes can make it too. Oxygen, likewise, can appear from simple reactions caused by sunlight on a water-rich world. That's why scientists are careful not to declare life found based on any single molecule or measurement. Instead, they look for patterns or an unusual blend of chemicals that suggest something interesting or unexpected is happening. Something else that comes up a lot in habitability discussions is the role of a planet's history. How old is it? How much time has it had for life to develop? And what has its climate been like? On Earth, life showed up relatively quickly after the planet cooled down, but it took billions of years before complex life became common. If an exoplanet is too young, it might be too unstable for life to begin or survive. If it's too old, a runaway greenhouse effect or a loss of its protective atmosphere could wipe the slate clean. The age of the star and the amount of steady warmth it delivers matter just as much as the planet's own characteristics. Moons and companion planets are another twist. For example, Earth's moon likely played a role in stabilizing our planet's tilt, which helped keep the climate relatively steady over long periods. Supersized planets in a system could act as cosmic shields, drawing away asteroids or comets that might otherwise blast the habitable zone. It's also possible that rather than needing to orbit a star, some planets, and maybe their moons, could have sources of heat below the surface, such as radioactive decay or tidal heating. In our solar system, moons like Europa and Enceladus have oceans beneath their icy shells, kept liquid by the gravitational pull of their parent planet. That raises the idea that maybe life could exist in dark, subsurface oceans, even if those worlds aren't in any star's habitable zone at all. Climate models are key for helping predict which exoplanets might be comfortable for life. Scientists use huge computer simulations to see what happens when you tweak atmospheric pressure, greenhouse gases, and the amount of sunlight received. Some studies suggest that with the right mix of heat and humidity, even planets a little outside the traditional habitable zone could maintain liquid water for long periods, especially if they have thick atmospheres or reflect lots of their star's energy away. Clouds, land-ocean distribution, and even the planet's rotation rate can all make a big difference in surface conditions. Astronomers also consider planetary mass and gravity as they think about habitability. If a planet is too small like Mars, it can't hold onto its atmosphere and loses surface water over time. If it is too massive, gravity can keep hold of a thick gas envelope, turning the world into a mini Neptune with crushing pressures at the surface. Probably bad news for life as we know it. There is an apparent sweet spot, maybe 1 to 2 times Earth's mass, where a planet can keep an atmosphere for billions of years without it getting too heavy and dense. Then there is the question of the star's stability. Some stars go through cycles of sunspot activity and flares, blasting out high-energy radiation that can strip away atmospheres or sterilize planetary surfaces. This is especially true for those small, red dwarf stars. Their planets could have enough warmth for liquid water, but constant flares might make life struggle or only survive underground. Brighter, more massive stars can be steady, but they also don't last as long, burning out in a few 100 million years. Our own sun falls in that comfort zone, stable for billions of years and not too intense. Astronomers are learning to pay close attention to these long-term stability factors as they figure out which exoplanets could hold life. It's interesting that as more results come in, the number of potentially habitable exoplanets keeps shifting. Early on, many planets were thought to be in the right zone, but later analysis showed they were too big, too small, too hot, or too cold. Only a handful so far are close enough in size to Earth and sit in that narrow band considered just right around their stars. Still, with each year and each new survey, more candidates show up, and planets in the habitable zones of red dwarfs are now among the most common types found in our galactic neighborhood. Earth analogues, planets that are as similar as possible to our home world, remain the top targets for many astronomers. They focus on stars with about the same mass and makeup as our Sun, hunting for rocky worlds in one Earth-year orbits. The idea is, if we can find even one planet with the right mix of water, atmosphere, and gentle warmth, it could tell us a lot about how common life might truly be in the galaxy. TESS, Gaia, Kepler and others have been able to sample only a small corner of the Milky Way so far, but the sample is getting bigger every year. Several planned telescopes and space missions are designed to find even more potentially habitable worlds. Instruments like the Extremely Large Telescope, ground-based 30-meter telescopes, and future direct imaging missions could offer fresh lists of planets for study, maybe even photos and atmospheric spectra for those closest to us. The search for life also prompts a look at what counts as a sign of habitability. It is not just about water or air. Some scientists are investigating geochemical cycles, plate tectonics, or evidence for volcanism, since these are thought to be part of what keeps Earth's climate stable over long time spans. There is work going on to better understand whether planets without tectonics but rich in volcanic gases, or those with stable, rocky continents but little geological movement, could support life at all. Even questions like, is plate tectonics common or rare among planets, could shift how many habitable worlds we believe are out there. For all the progress, it is worth remembering that so far no one has found convincing, direct signs of life anywhere outside of Earth. What scientists have found are a growing number of planets in or near their star's habitable zone, with sizes, orbits, and environments that make them interesting targets for study. Over the next decade, advances in both observing technology and computer modeling could bring a surge of new candidates, and possibly the first strong evidence that a planet out there really is alive, at least in some basic microbial way. Examining the wide sweep of exoplanet discoveries makes it clear that life might thrive in more places and more conditions than we see here. Some researchers are developing new habitability indexes that rank planets by their temperature, size, star type, possible atmosphere, and more. Others are looking for unusual patterns of starlight that could be markers for artificial life or advanced technology, boldly expanding the search beyond just microbes. Finding out how easily life gets started and how long it can survive under different circumstances is one of today's biggest scientific goals. Each new exoplanet offers fresh data for researchers to test their ideas about everything from the chemistry of ocean formation to the effects of solar flares. The picture that's emerging is exciting but also complex. Life, it seems, might need a narrow set of conditions, or it might arise almost anywhere, given enough time, energy, water, and the right chemistry. Future missions might soon make it possible for astronomers to start answering these questions with real evidence. So, when thinking about the search for life and the meaning of habitability, it comes down to a delicate balancing act. You need the right distance from the star, but also a stable climate, protection from radiation, enough gravity to keep air and water, and not too much to crush everything flat. You have got to factor in the quirks of the star and the planet's own past, from how it formed to whether it has hung on to its original stash of water and gases. Each time an exoplanet is found in this sweet spot, scientists look closer and try to figure out if it might be a place where something lives or where life could one day take hold. What they are learning is that the universe is bursting with possibilities, each one a candidate in the ongoing search for life beyond Earth. Because every time scientists get closer to identifying a potentially habitable world, it brings up an even bigger question. How unique is our own Earth in this whole cosmic sweep of planets? With thousands and thousands of confirmed exoplanets on the record, it sometimes looks like the galaxy is swimming in worlds. But even with so many options, none yet found match Earth in every crucial way. This keeps stirring up a debate in science, whether Earth is just one lucky example in a huge population, or actually rare in ways we are only beginning to grasp. To understand what makes Earth possibly rare, it helps to look at all the little and big things that come together to support life here. For starters, Earth sits in just the right spot from the sun, not too hot, not too cold, so liquid water can pool on its surface. Its atmosphere is thick enough to retain that water and filter out much of the sun's harmful radiation, and there's a protective magnetic field generated by the movement of molten iron deep inside the planet. Plus, the presence of a large moon works like a stabilizer, keeping the planet's tilt more or less steady over long stretches of time, which in turn helps regulate the seasons and climate. Some scientists argue that this set of conditions is more than just a happy accident. The rare Earth hypothesis, first outlined in the late 1990s by Peter Ward and Donald Brownlee, suggests that complex life requires a perfect storm of factors, some of which might be quite uncommon in the wider universe. For example, our planet's plate tectonics continually recycle materials between the crust and the mantle, regulating greenhouse gases like carbon dioxide and helping stabilize the long-term climate. That is not something we have direct evidence of on most exoplanets, though some indirect clues from atmospheres and planet sizes hint at a range of possibilities. Also, there's Earth's long period of geological calm. Our solar system, at least for the past several 100 million years, has avoided major cosmic catastrophes like nearby supernova blasts or frequent impacts from large asteroids. The giant planets Jupiter and Saturn probably help by acting as cosmic vacuum cleaners, sweeping up or deflecting chunks of material that might otherwise bombard Earth. Having this kind of shield might help give a planet a better shot at staying habitable over billions of years, giving life time to develop from simple microbes to complex animals and plants. When researchers look for exoplanets, they keep all of these features in mind. They are on the lookout for planets with similar size to Earth, similar orbits in the habitable zone, maybe signs of an atmosphere, and for those few close enough to image, maybe even hints of water or something similar on the surface. But one of the main challenges is that these details are hard to detect from so far away. Most planets found so far are either bigger or smaller, orbit much closer or much farther from their star, or circle stars that are much dimmer or much more active than our Sun. Statistically speaking, planets close in size to Earth are not especially rare. Surveys using the Kepler Space Telescope have shown that small, rocky planets are actually quite common in our galaxy, especially around red dwarf stars. Yet, there is a gap. While something about Earth's size pops up regularly, the trick is matching all the other ingredients. Just because a planet is the right size does not mean it has water, plate tectonics, a moon the size of ours, or a mild and stable climate for billions of years. Another thing that stands out is the kind of star a planet orbits. Our Sun is a middle-aged G-type star, not too hot or cool, and relatively quiet in terms of surface activity and flares compared to many others in the galaxy. Most of the stars in our cosmic neighborhood are actually smaller, dimmer red dwarfs. Some scientists think that planets orbiting these red dwarfs, even if they are the right size and temperature, may have a harder time supporting life because of intense radiation and wild flaring that can strip away their atmospheres. Larger and hotter stars, meanwhile, burn out much faster, faster, meaning there might not be enough time for complex life to develop on their planets before the star changes. Earth's plate tectonics is also a big question mark. This slow shifting of continents and the recycling of the crust into the mantle help drive important cycles of carbon, which keeps the temperature stable enough for oceans to exist over geologic time. Mars doesn't seem to have active plate tectonics anymore, and neither does Venus. On rocky exoplanets, it is still unknown how common this process is, but it could be key in deciding which worlds really get to be as stable and life-friendly as Earth. There's also the debate about Earth's magnetic field. Produced by the churning of liquid iron in the planet's core, the magnetic field acts as a shield against the solar wind, charged particles that otherwise might strip away the atmosphere and any water near the surface. Mars lost its magnetosphere billions of years ago and then lost most of its air and water. Venus has a weak field and a thick, toxic atmosphere. Some exoplanets could have lost their magnetic fields early on, which would mean a surface blasted by radiation. Understanding which planets have active, protecting magnetic dynamos is still a tricky measurement, but more sensitive instruments in the next decade might be able to give us hints. The presence of a large moon is another factor people often overlook. Earth's moon is unusually big compared to the planet, and it is thought to have formed from a massive impact with another body billions of years ago. The moon helps keep Earth's axial tilt stable, which in turn keeps the climate from wobbling too wildly. While a few exoplanet candidates have shown hints of possible moons, so-called exomoons, none have been confirmed at even close to the scale of Earth's moon yet. It is still being studied whether large moons are rare or just hard to find with current technology. Climate stability also involves more than one factor acting in concert. Volcanic outgassing can add greenhouse gases like carbon dioxide or methane to the air, while rock weathering and plant life pull them out again. Negative feedbacks, where one process cancels out another, have helped keep Earth from turning into a snowball or a desert oven over the eons. Changes in tilt, orbital shape, and even the sun's output also play a role. For planets without these stabilizing feedbacks, it might be much easier to swing into extremes, either freezing solid or boiling away the oceans. When scientists simulate what it takes to get another Earth, the models show that the odds can depend on even more details. What chemicals are in the planet-building disk? How many radioactive elements are present to heat the core? What the early atmosphere consists of, and when and how water arrives, either by delivery from comets and asteroids or from icy grains during the planet's formation. Each step is another roll of the dice, and sometimes models end up with worlds that are dry, too massive, soggy ice balls, or barren rocks, even when starting with similar conditions. Despite these challenges, researchers keep finding planets that get tantalizingly close. There are planets only a little bigger or smaller than Earth, sitting right in their star's habitable zone. TRAPPIST-1e, Proxima Centauri b, and several others have gotten a lot of attention for being sort of Earth-like. But in each case, something does not quite line up. Maybe they orbit red dwarfs rather than sun-like stars, have different day lengths, or we still don't know enough about what is happening on the surface. For now, there isn't a single planet that checks every box the way Earth does. Some scientists suggest that what we really need is a better understanding of how often life actually starts and what makes it keep going. Earth's history shows that early life appeared relatively soon after the surface cooled enough for oceans, but multicellular life took several billion years to get going. If complex life needs a super-stable climate and a protective magnetic shield, the odds do look long, but we have only one living planet to use as an example right now, which makes separating the rare from the common pretty tough. Researchers use all sorts of observations and models to estimate the odds for another Earth. For instance, the likelihood of a rocky, Earth-sized planet in the habitable zone goes up for red dwarf stars, because those are by far the most common stars in the galaxy. But, as mentioned, those systems have their own problems. The rare Earth camp sticks to the idea that the odds of getting everything right, proper star type, right orbit, enough water, steady climate, lack of deadly asteroid impacts and more, make true Earth twins a real long shot. Others argue that with hundreds of billions of stars in the Milky Way, even those long odds still mean there should be plenty of other Earths out there, just waiting to be found. The search is going wider and deeper with every new mission and telescope upgrade. Scientists are not just looking for atmosphere and water, but also building up databases of host star metallicity, age, activity, and more. They are also interested in planetary systems where the arrangement of planets, or the presence of gas giants at just the right locations, might have a protective or destabilizing effect on inner, potentially habitable worlds. Some researchers think the next big find could come from spotting the subtle fingerprints of life, the so-called biosignatures, in the spectra of exoplanet atmospheres. The challenge is, every possible sign of life can also have non-biological explanations. Only by getting as much information as possible about a planet's chemistry, temperature, history, and system can we even begin to say whether another world is like Earth or truly unique in some way. A newer idea gaining traction is that habitable planets might come in types, not just a single Earth template. Some could be water worlds covered in global oceans, while others might be super-Earths with thicker air and higher gravity. There might even be habitable desert worlds or tidally locked planets with temperate zones around their twilight zones. The definition for what makes a planet truly Earth-like is getting broader, but the search still puts our home as the clear standard. This question of Earth's rarity is not just academic, it shapes how we think about our place in the universe, where we aim telescopes, and what future missions are funded. If true Earth twins are extremely rare, some scientists argue we need to value what we have even more. If they are common, it fuels the hope that life, and maybe even intelligent life, will turn out to be a natural part of the galaxy. Either way, it keeps the field honest and focused on designing better ways to test every idea and build up a fuller statistical picture. When news headlines say, "Earth-like planet found," it's important to be careful. Usually, what that means is the planet is about the same size, maybe in the right orbit, but without many more clues about its atmosphere, geology, magnetic field, history, or surface. For now, the only place with all those features confirmed is right beneath our feet. Still, the more worlds we find, the more new twists and curves show up. It could turn out that some factors making Earth special are not so rare at all once we can look harder and more closely. Or it could be that our home really does sit at a kind of cosmic crossroads with a history and setup that's uncommon across the billions of stars out there. That is why scientists keep analysing all these variables, from planetary chemistry and star stability to the hidden histories written in rocks and air. Each new detection, each new model, and each rethink of the data moves the line a little, suggesting new strategies for the search. Some hope future technology will crack open the secrets of the closest stars, maybe even snapping details of continents, seasons, or signs of ecosystems on a distant twin. No matter how this shakes out, the rarity or uniqueness of Earth remains one of the biggest scientific puzzles going. Every confirmed planet, every spectrum, every bit of starlight captured draws us a step closer to figuring out our planet's place in this enormous, ancient galaxy. Whether Earth turns out rare or is just a sample of what's possible, understanding these odds helps us see both the preciousness of our own world and the full sweep of what nature can put together, given time and all the raw material the universe has to offer. That curiosity about whether Earth is unique leads right into one of the liveliest areas in exoplanet research today, learning about exoplanet atmospheres and hunting for biosignatures. This work goes much further than just finding out where a planet is or how big it might be. The focus is on figuring out what the planet is actually like, from its weather down to its chemistry, because that is where we can start really asking if some of these distant worlds could support life or maybe even already have it. Atmospheres are basically the blanket of gases that surround a planet. On Earth, our atmosphere has oxygen, nitrogen, some carbon dioxide, water vapor, and a small amount of other stuff. It helps keep our world warm through something called the greenhouse effect and protects us from too much radiation from the sun. For a long time, people figured that planets outside our solar system would have atmospheres too, but the real question was how to detect them. Since you can't just see a planet's air from hundreds or thousands of light years away, getting even a glimpse at what those atmospheres are made of is a huge piece of the puzzle. The first step to studying an exoplanet's atmosphere usually comes from the transit method. When a planet crosses in front of its star, some of the starlight passes through the thin layer of gases at the edge of the planet, that is, through its atmosphere down near the horizon. Each kind of gas blocks or absorbs the starlight in its own way, so if you split the light into a rainbow, which scientists call a spectrum, you can often spot little dark lines or bumps where a particular gas takes a bite out of the light. This is called transit spectroscopy, and it is why astronomers are so interested in finding planets that transit their stars from our point of view. The bigger and fluffier the atmosphere, the easier it is to see its effect. Most of the early exoplanet atmosphere discoveries came from hot Jupiters, which are huge gas giants orbiting close to their stars. These planets have big atmospheres full of things like hydrogen, helium, sodium, and sometimes even clouds of vaporized iron or silicates. The Hubble Space Telescope was the first to spot the signature of sodium in an exoplanet's atmosphere this way back in the early 2000s, and from there, the field just exploded as more powerful telescopes came online. Detecting atmospheres for smaller, rocky planets has been a lot harder, but that is just beginning to change thanks to new technology. The James Webb Space Telescope, which started science operations in the year 2022, is picking up the faint fingerprints of molecules even on some planets close to Earth in size. Webb can look in the infrared part of the spectrum, that is, the kind of light that carries a lot of heat, which helps pick out signals from water vapor, carbon dioxide, methane, and even more complicated molecules if they are present in enough quantity. Every new spectrum is a mix of excitement and caution though, because it takes a lot of fine-tuned analysis to know you are not just seeing something in the star itself or in dirt and dust between us and the exoplanet. Atmosphere studies are not only about what gases are there, but also about structure and dynamics. Is the atmosphere thick like Venus, thin like Mars, or something in between? Are there clouds, winds, or big storms that change how the atmosphere looks from one side of the planet to another? By watching how the atmosphere changes during transits, or how the planet glows or reflects light as it orbits around its star, astronomers can make basic maps of temperature and even weather on these far-off worlds. There is another trick called secondary eclipse spectroscopy. When a planet passes behind its star, any infrared light from the planet disappears until it pops back out the other side. By comparing the system's light just before and just after the planet is hidden, scientists can measure the emission from the planet itself, which tells them things about the planet's own temperature and the makeup of its atmosphere. This approach works best for hot, bright planets, but is being improved to work for smaller, cooler ones as instruments become more sensitive. One big reason atmosphere studies are so important is that some combinations of atmospheric molecules can only persist if they are constantly replenished, often by living things. These are the famous biosignatures, chemical signals that might point to biology at work. On Earth, one of the strongest biosignatures is free oxygen because it reacts so easily with rocks and other chemicals that it would vanish from the air if plants, algae, and bacteria did not keep making more. Methane is another good example. On modern Earth, most methane comes from life, both microbes and animals. If you spot both oxygen and methane in the same place and time, that is even more interesting, since those two gases like to destroy each other. Their continued presence together would suggest something, potentially life, keeps making both. The main challenge is that planets are complicated places, and plenty of natural, non-living processes can also make some of these same gases. A planet with a lot of volcanic activity could spit out methane or sulfur compounds without any life, just from heat and chemistry underground. Free oxygen could show up if a planet is bombarded by strong ultraviolet light, breaking apart water molecules and leaving oxygen behind. The really big challenge for finding a true sign of life is not just spotting a single gas, but finding a special blend in the right amounts that is hard to explain without something alive producing it. This is why teams working on atmosphere measurements are building up a list of false positive scenarios, combinations of geological or chemical pathways that could mimic signs of life. Part of the work now is not just looking for the right signals, but also proving that a world with a lot of methane or oxygen or some other interesting gas is not just going through a weird lifeless phase. The hope is to spot cases where the balance of gases looks out of whack in a way that almost always points to biology. Aside from gases, the way a planet's atmosphere interacts with light can show clues to surface conditions. For example, a thick, hazy sky might hint at a planet shrouded in hydrocarbon smog, like Saturn's moon Titan. High-altitude clouds made of silicate, iron, or even more exotic materials show up in the spectra of hot Jupiters and some other ultra-hot exoplanets, suggesting temperatures that can vaporize rock. Some atmospheres seem loaded with water vapor, which could mean clouds and seasons, or even rain of a sort. Some high-profile results have come in recent years, such as signs of water vapor in the atmospheres of a few small exoplanets located in their stars' habitable zones. One example is K2-18b, an exoplanet that sits about 110 light-years from Earth. In 2019, researchers found the signatures of water vapor using data from the Hubble Space Telescope, along with hints that the planet's atmosphere might be thick enough to allow for clouds and possibly even liquid water below. However, this planet is much larger than Earth, more like a mini Neptune, so whether it is truly habitable for life, as we know it, is still up in the air. Another recent flare-up of interest was about the possibility of phosphine in the clouds of Venus. While not directly about an exoplanet, the story shows how difficult it can be to interpret potential life signatures and why independent checks and repeat observations are so important. The phosphine result led to calls for more careful atmosphere studies and even more skepticism until enough data can be gathered to make a confident claim. For now, Earth remains the one planet with an atmosphere known to support life, so it serves as the template for most of these searches. Scientists use what they know about how biological processes on Earth shape our own air, and then look for similar patterns or knock-on effects that might appear in exoplanet atmospheres. Researchers also run many simulations, fake, computer-generated planets, to see what atmospheres would look like for different kinds of life, planets, and chemistry. These models help decide what to look for in real data. Even as more planets show up, getting detailed atmospheric spectra remains tough work. The best measurements only come from planets that either transit often or are close enough to get good images. Clouds, dust, and even our own atmosphere on Earth can get in the way of good data. This is why a lot of effort now is aimed at building new, ultra-sensitive telescopes on the ground and in space, like the Extremely Large Telescope in Chile, or possible future missions like LUVOIR and HABEX designed by NASA and the European Space Agency. These projects are all about scaling up the search, going from just giants and warm planets to cooler, smaller, more Earth-like worlds. There are also efforts to cross-check what is found in atmospheres with other clues about a planet. That means comparing atmosphere results with movement data, the presence of moons or rings, or even the brightness changes as planets rotate. The idea is to put together a picture where the chemistry, physics, and movement all make sense together, not just one hint or signal. Atmosphere work is also key for figuring out what may make a planet uninhabitable. If a world has too much carbon dioxide or a runaway greenhouse effect, that can tip it into becoming a hellish planet like Venus. If it is missing an atmosphere entirely, like Mercury, there will be nothing to keep water liquid or protect life from stellar radiation. Mapping the atmospheres of as many planets as possible helps build up a map of where life as we know it would be possible, and where only more exotic forms could survive. This line of study is now reaching beyond individual planets to look at patterns across the thousands of known exoplanets. Astronomers have found that small, rocky exoplanets close to their stars often have thin or missing atmospheres, probably because radiation has stripped them away. Slightly larger worlds, super-Earths and mini-Neptunes, might keep thick atmospheres, but those could be more like the air on Uranus or Neptune, made of hydrogen and helium, and not too friendly for life as we know it. Understanding why some worlds keep their air and others lose it is a growing area of research tying together planet size, orbit, star type, and more. Weather is another hot topic. Some exoplanets on tight or in highly tilted orbits experience wild seasonal changes. The day side might be scorched, while the night side freezes. Some have world-spanning winds faster than anything seen on Earth, driven by extreme temperature differences. Others might have clouds and even rain made of iron, glass, or rubies, depending on local conditions. Weather and climate both shape and are shaped by the thickness and mix of gases, the planet's rotation, and the energy it receives from its star. One fascinating angle is the idea of using clouds as a probe of what's going on below. On Earth, certain cloud types only form under tight conditions of temperature and humidity. If astronomers can resolve cloud layers in an exoplanet's atmosphere, it could point to underlying oceans, continents, or even seasonal cycles. The challenge here is that clouds tend to blur or block some of the main signature molecules, making it harder to pin down the chemistry underneath. Another layer to this puzzle involves atmospheric escape, how and why planets lose their gases over time. Young, active stars are especially good at blowing atmospheres away with solar wind and ultraviolet light. Planets with weak gravity or without magnetic fields also tend to lose air faster. This is one clue to why so many small planets detected by missions like Kepler have thin or missing atmospheres compared to larger planets farther from their stars. There are big plans for how the search will move forward. Many teams are now focused on nearby star systems, hoping to pin down the atmospheres of planets that, while not exactly Earth twins, are close enough in size or temperature to be interesting. Others are casting the net wide, building up databases of different exoplanet atmospheres to look for trends and outliers. Over the next decade, astronomers hope to collect enough examples to spot which combinations of air, water, and chemistry signal a truly special planet. Another promising sign is the development of machine learning tools to sift through mountains of data coming from all these new instruments. These programs can flag unusual patterns that might slip past human eyes and help sort out which signals are worth a deeper dive. With future telescopes set to bring back 10 or even 100 times as much data as today's missions, this automation will only become more important. Place all of this together, and studying exoplanet atmospheres is one of the keys to answering if we are alone. Detecting biosignatures, if and when it happens, will be a careful, step-by-step process. Each new molecule and pattern in a planet's air will have to be checked, cross-checked, and discussed to make sure nothing else could explain what is being seen. As the list of known worlds keeps growing, the chances go up that there will be a planet out there with the right mix of chemistry, distance from its star, size, and history to possibly show real signs of life. With each step forward in measuring exoplanet atmospheres and interpreting potential biosignatures, astronomers can fine-tune where they point the next telescopes and which planets become the next big targets for observation. The more they learn, the more they are shaping how future missions will be designed, what questions will be asked, and what technologies need to be developed next. It is a picture that is getting sharper and more colourful every year as more discoveries come in, raising hopes that somewhere in that mix of air and light, the first real sign of life beyond Earth is waiting. That whole effort to read the secrets of distant atmospheres depends on understanding how these planets even came to be, and that is where the latest ideas about planet formation and migration come into play. For a long time, most of what people thought about planet formation was shaped by our own solar system. The classic story goes like this. A cloud of gas and dust spins around a newborn star. Bits of material start sticking together, small clumps become bigger clumps, and eventually, after millions of years, you get planets. The rocky ones end up close to the star, where it is warm and ices cannot easily form, while the gas giants show up farther out, where things are cold enough for hydrogen, helium, and other gases to pile up into giant balls. That model, based on Earth, Mars, Jupiter, and the rest, was the backbone of astronomy textbooks for decades. Detecting thousands of exoplanets changed almost everything about that picture. The very first exoplanets that astronomers found around Sun-like stars were not neat analogues of Jupiter or Saturn sitting far from the heat. Instead, they found giant planets, often even bigger than Jupiter, orbiting scorchingly close to their stars. Some of these hot Jupiters have years that last only a few Earth days, finishing an orbit in less than the time it takes most people to finish a novel. That shook up theories fast, because none of the basic planet formation models at the time could easily explain how a gas giant could even exist that close to a star. The temperatures there should have been too high for the giant planet to hold onto the gas it needs to grow. So, to make sense of these new findings, scientists started digging into the details of planet formation and realized that the process is a lot messier. Planets do not just form where we find them today. A key updated idea is planet migration. The thinking goes that many planets actually start out in one part of a solar system and then move, sometimes over billions of years, sometimes much faster. This happens because the huge disk of gas and leftover dust that surrounds a young star is not a calm, quiet place. Gravity from the star, other planets, and even nearby sibling stars can push and pull on newborn planets, nudging them inward or outward. Two main ideas describe planet formation: core accretion and disk instability. Core accretion is the more widely accepted of the two for most planetary systems. In this scenario, tiny grains of dust in the protoplanetary disk, that's the leftover stuff from the star's birth, gently stick together through electrical and chemical forces. Over time, these grains grow into pebbles, then boulders, and eventually into kilometer-sized planetesimals. These bodies keep colliding, sticking, breaking apart, and reforming until some of them get big enough, maybe 10 times the mass of Earth, to pull in gas directly from the disk. That's how you get gas giants like Jupiter and Saturn. Disk instability, on the other hand, is more dramatic, but might also help explain certain huge planets found far from their stars or very quick formations. In this version, part of the gas disk gets so cold and dense that it collapses under its own gravity, forming a big clump in just thousands of years, much faster than the slow and steady model of core accretion. That could create a huge planet, even one many times the size of Jupiter, before the heat from the star or the energy from the disk's movement has the chance to blow away the gas. Both models might be true in different environments, depending on the initial conditions around a star as it forms. Migration became a central piece as astronomers tried to make sense of all the super close-in planets being found by missions like Kepler, TESS, and ground-based telescopes. Planets can migrate when their gravity interacts with the disk, creating waves and ripples that push the planet along. If the planet is big enough, like a proto-Jupiter, it can carve a gap in the disk and then slowly spiral either inward toward the star or outward further away. Smaller planets might move around more unpredictably, sometimes smashing into bigger planets, getting ejected from the system, or simply getting pulled or pushed by others nearby. In the early years of a star's life, its disk of material only lasts a few million years, so this migration phase has to happen relatively quickly. Once the gas and dust are gone, planets normally stay more or less in place, except for rare events like a passing star stirring things up. This can lead to the types of arrangements we see with exoplanets, some systems with tightly packed planets, others with big gaps, some with lone hot Jupiters close to the star and empty space farther out, and others with planets tossed out into deep space as rogue planets, not attached to any star. Some interesting examples of migration show up in the weird orbits of certain known exoplanets. A lot of discovered hot Jupiters have orbits that are tilted relative to their star's equator, or even orbit the opposite direction to the star's spin. That is a huge clue that something dramatic happened during their migration. The leading idea is that at some point, another planet or a nearby star changed the gravitational balance, sending the planet plunging inward or flipping its orbit. Sometimes there are leftover signs, other tilted planets, debris disks knocked at weird angles, or gaps where a planet might once have been before being tossed out. The process of forming rocky planets like Earth and Mars has its own quirks. These planets probably form in the frost line area, close enough to the star that it's warm but far enough out that metals, minerals, and some ice can exist. As mini-planets crash together and merge, each impact can change the chemistry, make the planet spin faster, or trigger the start of volcanoes and tectonics that help shape the surface. Some collisions are so huge that they can blast off big chunks, like the giant impact that probably formed our moon about 4.5 billion years ago. Migration and these giant impacts might explain why so many planetary systems do not look anything like ours. In many systems, there's evidence of hot Jupiters that may have ploughed through the disk, scattering smaller planets inward or outward, or even swallowing them up. Some systems have chains of super-Earths or mini-Neptunes all jammed together in a way that never happened here. Others are just as strange, systems with one giant far out, a few tiny rocky worlds up close, or no obvious pattern at all. Every new planet found gives researchers another test case for planet formation and migration models. Astronomers have also begun to look for the fingerprints of planet formation and migration in the disks themselves. With telescopes like ALMA in Chile, they can see gaps, rings, and spiral patterns in young disks that seem to show where planets are starting to sweep up material or carve paths. Some images even show shadows and warps caused by planets moving off the main plane of the disk. One of the more surprising things is how planetary systems can appear stable for billions of years but still end up reshuffled. This can happen after the gas and dust are gone. Even small nudges or gradual changes from remaining material or distant sibling stars can trigger what is called instabilities. Planets might bump each other, shift orbits, or even get slingshot out of the system. In our own solar system, models suggest that the giant planets might have moved around quite a bit early on, with Neptune and Uranus likely drifting outward and Jupiter inching further from the Sun, all while flinging leftover icy objects into the Kuiper Belt and Oort cloud. The presence of other stars in the neighborhood can also affect planet formation and migration. Many stars form in clusters or with companions, and the gravity from these other stars can stir up the disk, making some planets migrate faster or be ejected completely. In crowded star-forming regions, this process might set a limit on how many planets survive and where they end up. There is still so much we do not know about when and how migration takes place. Computer simulations help astronomers test different setups. How big does a planet need to be to carve a gap? How do multiple planets in resonance avoid knocking each other out? What does migration do to the distribution of water and other building blocks that get delivered to rocky worlds? These are the kinds of questions that are tackled by teams around the world using powerful models and more data from the ever-expanding exoplanet catalogues. Migration theories also intersect with questions about habitability. A planet might start in a place too cold or too hot, but if migrating planets move into the habitable zone, it's possible that planets could have long enough in the right conditions for life to start. Migration might even bring in extra water from icy worlds farther out, as comets and asteroids are nudged inward by the movement of larger planets. The composition of a planet's atmosphere, its water supply, and even its long-term stability could all be determined by how and where it formed and whether it moved. It is a big deal for anyone asking how likely it is for life-friendly planets to exist elsewhere. Observations keep coming in that push the limits of these models. Astronomers are now able to measure the chemical fingerprints of exoplanet atmospheres and even the starlight blocked by protoplanetary disks in other star systems. Every time a new anomalous planet is found, a super-hot Neptune, a puffy Jupiter on a 2-day orbit, or a system with rocky planets tightly locked in resonance, the formation models get refined. There are also big implications for the story of water and organics, the things most important for life. In our own solar system, it looks like much of our water may have come from impacts by icy bodies migrating in from the outer regions. If hot Jupiters or other large planets migrate through their systems early on, that movement could sweep up water and organic material, or deliver them to rocky worlds closer in, directly affecting how likely those inner planets are to end up with oceans. Our growing list of exoplanet discoveries keeps feeding new surprises into these debates. The diversity of systems, some balmy and packed with planets, others icy and empty, shows just how sensitive planet building is to all the crazy details: original disk size and chemistry, the number of planets, nearby stars, and chance events like collisions and ejections. As the next wave of telescopes comes online, from Webb to the extremely large telescope, the data flood will let scientists test some of these theories on bigger and better samples. For example, by comparing the orbits, masses, and even the elemental ratios, like carbon to oxygen, in hundreds or thousands of exoplanets, researchers can start to identify which trends are the most important, like whether heavy element-rich disks are more likely to produce hot Jupiters, or if certain types of stars are always surrounded by rocky worlds. Studying planet formation and migration is not just about making sense of orbits and sizes. It is about figuring out what stories lie behind the systems we see, why some planets are alone while others have siblings, and what all this means for the search for other Earths. Every simulation, observation, and discovery points to a universe that is more active and complicated than anyone would have guessed a few decades ago. So, the next time someone mentions a weird new exoplanet, it is a good bet that its history involves plenty of movement, rearrangement, and even a few cosmic close calls. Planet formation and migration explain how a collection of dust and rock can turn not just into one kind of world, but into the full, surprising menagerie of planets astronomers are now discovering all across the galaxy. Every new insight about how planets are built and shuffled adds another piece to the puzzle of why the systems we see look the way they do and what that might mean for worlds like our own. All this talk about how planets are formed and shuffled around in their systems really opens the door to one more area that has grown more important in exoplanet science: understanding the influence of moons and binary stars on planet formation, stability, and even habitability. When you start looking at the sky with newer telescopes, you quickly realize that planets almost never exist in isolation. Most stars in the Milky Way don't shine alone, like our Sun, but have one or more stellar partners. On top of that, the search for moons around exoplanets, called exomoons, is now one of the most exciting frontiers in the field, adding new layers to the already complex picture of how planetary systems are built. Let's start with binary stars. About half the stars you see with your naked eye are are binary systems, meaning two stars are gravitationally bound and orbit each other. Sometimes you even have multiple systems with 3 or more stars. For a long time, people thought planets would never survive in a binary system, or that any planet forming there would be quickly pulled apart by the ever-changing gravity. But observations by ground-based telescopes and missions like Kepler and TESS have shown this isn't true. There are planets called circumbinary planets that orbit around both stars together, and others where the planet orbits just one star, with a distant companion star in the background. The way these orbits work out is fascinating. In a circumbinary setup, a planet moves around both stars as if they were glued together, and from the planet, you'd see two suns shining in the sky. These orbits can be stable for millions or even billions of years, as long as the planet's path isn't too close or too far away from the stars. Kepler 16b is one of the best-known cases, discovered in the year 2011 orbiting a pair of stars about 200 light-years away. The two stars orbit each other every 41 days, and the planet takes just over 229 days to go all the way around both of them. It's a distant gas giant, not unlike Saturn, but it's living proof that binary star systems can host planets, and that these planets can have orbits that hold up over long timescales. Another arrangement is for planets to orbit just one star, but with a companion star orbiting much farther away. These are often called S-type orbits. The second star might be so far off that it looks just like a bright point in the planet's sky. These systems create zones of stability and instability. There are sweet spots where planets can have nearly circular orbits for billions of years, and other places where the combined pulls of gravity would toss a planet's path into chaos. Simulations show that even in the most crowded 3-star systems, there can be pockets where planets survive for a long time, though the chances go down as more stars are added to the mix. The presence of a binary or even trinary system changes the rules for how planets form as well. The dust and gas disks around young binary stars often get twisted into strange shapes, sometimes becoming warped, forming rings, or even getting split into separate blobs. These effects make it harder for planets to grow big, or to finish forming before being nudged out of place. Even so, astronomers have found that not only do planets form in these systems, but some of them can end up surprisingly Earth-like, orbiting in just the right distance for water to exist, if there's enough atmosphere. Planets in binary systems might also have unique seasons and climate patterns, because the changing geometry as the two stars orbit each other can cause the total amount of light a planet receives to fluctuate in complex cycles. This can create conditions that are very different from the steady sunshine Earth gets from the sun. Models suggest that circumbinary planets might experience weird double sunrises and sunsets, or have long periods of mixed daylight and night as the stars move in their dance. On the other hand, in S-type systems with a distant companion star, the tides between the two stars might help stir up the protoplanetary disk early on, helping bring more material in toward the planet-forming regions, or sometimes sweeping things away, depending on the details. This stirring can speed up planet formation in some cases, or limit it in others. Binary systems also affect planetary orbits over time through mechanisms known as Kozai-Lidov cycles. This is a process where the gravity from a far-off companion star can nudge a planet's orbit, making it more elongated or even flipping its tilt over long ages. That might be how some exoplanets end up with strange, highly inclined orbits, or get moved from a safe distance into a dangerous, close-in orbit that changes their temperature and even strips away atmospheres. Now, shifting to moons, the field is starting to open up in big ways. In our own solar system, we see a huge range of moons, some bigger than the planet Mercury, some orbiting gas giants in massive swarms, and a few like Earth's moon that are just the right size and distance to create tides and probably help stabilize a planet's climate. Some moons in our system have underground oceans kept warm by the pull of gravity from their host planet, as with Europa and Enceladus. These ocean worlds have become a big part of the conversation about where life might exist, because even in the icy darkness, the ingredients for life might be there. Finding exomoons around exoplanets is much tougher than finding planets themselves. Moons are smaller, dimmer, and their signatures can be easily confused with noise in the telescope data. But astronomers are making progress, searching for tiny wobbles and timing shifts in the way exoplanets pass in front of their parent stars. So far, there are a handful of promising candidates, with the most famous being a possible giant moon orbiting the Jupiter-sized planet Kepler 1625b, located about 8,000 light-years away. This candidate, still unconfirmed, would be roughly the size of Neptune, which is gigantic for a moon, making it much easier to spot than something the size of our own moon or smaller. Whether this and other hints prove to be real or just anomalies in the data is an open question that will take more observations from next-generation telescopes. Scientists expect exomoons to be common simply because many of the planet formation processes that build up big planets naturally throw off lots of smaller bodies, some of which should get caught in orbit as moons. If moons turn out to be large, stable, and have the right conditions, like an atmosphere or an internal heat source, they might even be habitable themselves, especially if they orbit giant planets within the habitable zone of their star or stars. There's also an idea growing among researchers called moon habitability. Moons could theoretically be as likely as planets to support life if they have all the right stuff: energy, liquid water, protective layers, and stability over billions of years. In science fiction, this has been a popular theme, but in the last few years, planetary scientists have developed models showing that under certain circumstances, moons could stay warm enough from tidal heating. That's the flexing and squeezing they feel from being so close to a giant planet, even when they're far from stellar warmth. If such moons are wrapped in a thick, protective atmosphere or have subsurface oceans, they could be targets for life nearly as intriguing as planets themselves. The presence of moons and the tidal effects they generate aren't just good for heat either. On Earth, our moon helps stabilize our planet's axial tilt, keeping the seasons moderate over long timescales. Tidal forces also drive ocean mixing, which distributes heat and nutrients and might have even played a role in the rise of life. If big exomoons are out there around extrasolar planets, especially rocky or water-rich ones, they might play similar roles: more climate stability, active geology, and other features that raise the odds for life. Some exoplanets could have ring systems even larger and more complex than Saturn's, maybe with dozens of small moons controlling and maintaining the ring's shape. While rings themselves probably aren't places for life, the presence of rings may tell us important clues about the age of a system, the formation history of its planets, and the evolutionary processes happening over time. There have been a few sightings of possible huge ring systems around giant exoplanets, for example J1407b, which appears to have a ring system hundreds of times larger than Saturn's, blocking out starlight as the planet passes in front of its star. The interplay between rings, moons, and planet stability is a fresh frontier too. In some cases, the gravitational tugs from big satellites can affect a planet's own shape, spin, and even atmospheric circulation. Some moons may eventually drift away or fall in over billions of years, changing the tilt or rotation rate of a planet, and possibly reshaping climate and habitability prospects over geological timescales. Looking at the larger picture, the influence of binary and multiple star systems, along with moons and rings, creates almost unlimited ways for planetary systems to organize and evolve. Binary stars can spread protoplanetary disks out in strange ways, produce wild orbit flips, or shelter compact groups of planets in stable spaces for billions of years. Moons may be common, rare, or even essential for the long-term survival of life on rocky worlds, depending on how the statistics play out as more systems are observed. All these dynamics, binary stars, moons, rings, tidal heating, make the search for habitable worlds even more complex, but also more exciting. When scientists model planetary climates, they now have to factor in the possibility of double suns, big moons changing tides, tilted disks creating unpredictable seasons, and the potential for habitable exo-Europas orbiting distant gas giants. Every time a new quirk is discovered, like an orbiting moon hinting at an ocean, or a planet surviving in the shifting fields of a binary, it adds another chapter to our evolving understanding of what planetary systems can be. What's clear is that the old idea that most stars are like the Sun and most planets are lone wanderers is just not true. The cosmos is full of binaries, trinaries, clusters, and even stars born in dense nurseries. And planets seem to find a way in almost all of those environments, even if their orbits, companions, or seasons are nothing like Earth's. The next decades of exoplanet discovery are likely to find everything from giant snowball moons on the edge of space to rocky circumbinary planets orbiting two suns. Researchers are watching for evidence that strong tides or multiple stars make planets better or worse places for life, whether they create more opportunities or make things so unstable that water and air can't last for long. There's new work, for example, on how the presence of a binary or a big moon can rescue a world from going snowball cold or overheating, essentially acting as a stabilizer and supporting long-term habitability. Teams are also exploring if moons could remain habitable as planets migrate, or if binary stars can maintain habitable zones over millions of years despite all the push and pull. Advanced telescopes arriving soon will be able to spot smaller moons and ring systems, even map the atmospheres or surface conditions of planets and moons in binary systems. If any of these places turn up markers pointing to water, chemistry cycles, or even biological activity, it will open up a whole new set of questions about how life can arise and where we should focus our search. Trying to figure out the role of moons and binary stars adds to our understanding of the full diversity of planetary systems, from the way planets and moons stabilize each other's orbits, to how rings might hint at hidden satellites or even unseen planets further out. These discoveries will help shape our search for habitable worlds, since some might only be possible in the presence of certain moons or in the right kind of binary arrangement. What's also becoming obvious is that every time scientists discover a new system, whether it's a planet with rings bigger than Saturn's, a world circling two suns, or a giant moon in a place no one expected, there are always more possibilities than anyone ever guessed. The presence of binary stars, exomoons, and rings doesn't just make the math harder. It shows that planetary systems are even richer, messier, and more adaptable than we ever dreamed. Each new layer lets us ask better questions about where life might pop up, how long it could survive, and what signs to look for as we scan the skies for the next surprising world. With all the complicated interactions between planets, moons, and multiple stars, and as astronomers keep discovering more and more diverse worlds, a pretty natural question pops up. If the galaxy is filled with planets, many inhabitable zones, and some with all the right ingredients, why haven't we seen any clear signs of life or intelligent civilizations elsewhere? This is where the so-called Fermi paradox steps into the spotlight. It's named after the physicist Enrico Fermi, who in the 1950s casually asked, "Where is everybody?" Given how many stars and planets are out there, many scientists, both then and now, find it puzzling that we don't see evidence of advanced aliens, huge interstellar networks, or even obvious distant radio signals. The numbers just make this more glaring. Rough estimates today put the number of stars in the Milky Way at around 200 billion or more. From what the Kepler and TESS missions have taught us, there might be just as many, if not more, planets, sometimes more planets than stars. In fact, it looks like nearly every star has at least one planet, and many have sizable families of worlds. Out of those billions of planets, millions could sit in the so-called habitable zone where liquid water is possible. The ingredients for life, water, carbon-based molecules, energy from stars, seem to be pretty common building blocks. With numbers like that, you'd think by now something, somewhere, would have made itself known in a big way. But as far as we can actually tell, there's silence. No unambiguous radio signals, no spacecraft, no signatures of vast alien engineering, no evidence from telescopes that anybody is out there building big cities or covering planets with technology. The galaxy is noisy in terms of natural sources, supernovae, pulsars, star flares, but extremely quiet when it comes to signs made by intelligent life. People sometimes call this the Great Silence or the Great Filter, and it's one of the big unresolved issues in modern science. To try and make sense of it, scientists break the problem into a lot of possible explanations. Some involve technological limitations on our side, some involve the nature or rarity of life itself, and some even suggest civilizations might hide or vanish. One explanation is that we just haven't looked long enough or with the right sensitivity. Most of our searches for signals, like those done by SETI, the search for extraterrestrial intelligence, have just barely scratched the surface, scanning only small areas of sky or only certain wavelengths of radio light. Earth's own radio bubble, our leakage of TV, radar and other signals, only extends about 100 light-years, which is a tiny patch compared to the full spread of the Milky Way that stretches across more than 100,000 light-years. It's also possible that intelligent aliens use technologies or communication methods we haven't even thought of or can't detect. Radio waves, which make sense to us, might not be their tool of choice. They could prefer narrow beams of lasers, neutrino pulses, or some other medium we haven't tried to pick up. Advanced civilizations might even use encryption or tight directional signals, making their presence practically invisible unless you're pointed right at them at the right instant. Apart from technology, there are other ideas about why the galaxy feels so empty. One of the major theories is that while simple life might be very common, think bacteria or algae, intelligent technological life is incredibly rare. Maybe you need billions of years of stable climate, just the right chain of evolutionary steps, and lots of lucky breaks to go from microbes to creatures that can build radios or rockets. If there are dozens of hard steps where things can go wrong, it might be that most inhabited worlds never get beyond the simple life stage. There's evidence on Earth for this being a tough process. Life appeared here about 3.5 billion years ago, but for much of that time it was just single-celled and fairly basic. Only in the last 500 million years did big, complex animals and plants show up. Intelligence, the kind that lets creatures manipulate their world and build technology, has been around for a tiny fraction of Earth's total life history. Another idea is that intelligent life might actually self-destruct before it can spread very far. Civilizations might wipe themselves out through nuclear war, climate disaster, out-of-control technology, or resource exhaustion before they can travel through the stars or even send lasting messages. This view makes the Fermi paradox a kind of warning. Maybe reaching the point where you can build advanced tools is easier than surviving their risks for long periods. Some call this possibility the Great Filter, meaning there's a stage in evolution that almost all life hits and usually can't get past. More optimistically, some scientists argue we just haven't been looking in the right way or the right place. Given the vast distances involved, even a nearby signal could take years or centuries to arrive. We only started broadcasting powerful radio signals a little over 100 years ago. For all we know, another civilization did the same 2,000 years ago, and their signals just haven't reached us yet, or past us before we started listening. It's also worthwhile to remember that the search for life is just getting started. Telescopes that hunt for biosignatures, gases in exoplanet atmospheres that would likely be produced by life, are only just becoming sensitive enough to do their job. The search for technosignatures, markers of advanced civilizations like huge artificial structures, laser pulses, or engineering projects on cosmic scales, is still in its early days. For now, we haven't spotted any Dyson spheres, theoretical megastructures built to gather energy from stars, or unexplainable heat patterns from distant star systems. Some suggest intelligent life might not be interested in contact. Civilizations could have rules, philosophies, or practical issues that keep them quiet or contained. Maybe there are zoo hypotheses, where advanced species observe us without making contact, or maybe isolation is standard practice to avoid trouble or interference. Alternatively, their version of technology might not leave big, detectable traces. If they mostly live virtually, underground, or use low-impact, eco-friendly tech, the signs might be almost impossible to pick up. People have also wondered if we might simply not recognize alien life even if we saw it. What if it's based on different chemistry, like silicon instead of carbon, or has forms and organizations totally unlike what anyone expects? For instance, alien civilizations might live in deep atmospheres of gas giants, under the ice of frozen moons, or in habitats on worlds that are nothing like Earth. Their technology, biology, and communication might hide in spectral gaps we are not focusing on, or use timescales much longer or shorter than human lifespans. Sometimes, astronomers look for rare, powerful events that could be signs of technology, like fast radio bursts, which for a while sparked excitement as possible technosignatures. But in case after case, scientists have found natural explanations, such as magnetars or neutron stars acting up. The universe is full of energetic phenomena that are dramatic, but not evidence for life. It's also possible that life existed elsewhere and simply isn't around anymore. Maybe civilizations rise and fall over millions of years and their traces are gone by the time anyone else shows up. Catastrophes like supernovae, gamma-ray bursts, or impacts from space debris might regularly sterilize large stretches of the galaxy. Planets themselves might change over eons, with unstable climates or geological change wiping out life before it can go interstellar. Some try to break down the odds of detecting life using something called the Drake equation, a formula from the early 1960s. It multiplies together guesses for the number of stars, the rate at which stars form planets, the number of those with habitable worlds, the odds of life appearing, the chance of intelligence developing, the odds those civilizations communicate, and how long they last. Adjusting these guesses changes the outcome from almost nobody else existing to potentially thousands or millions of galactic civilizations. Over the years, more and more terms in the formula have become better known, like how many stars have planets or what fraction of planets are rocky. But the parts about life starting, intelligence, and technological sieves remain giant unknowns. Researchers keep finding new places to look, though. The hunt for biosignatures has ramped up with new telescopes that can measure the atmosphere of exoplanets. The hope is to spot strange mixes of gases, like oxygen and methane together, that stand out from purely geological processes. If a planet shows those signs, it could point to active biology, even with nobody sending signals. Meanwhile, the field of technosignatures is getting creative, looking for things like regular pulses of light, like distant laser flashes, unusual heat or infrared excesses in odd stars, or even patterns in atmosphere or planetary cycles that couldn't happen naturally. The Fermi paradox will stick around as more data comes in. As instruments get more sensitive and sky surveys go deeper, the absence of clear, deliberate signals will either start to change or become more puzzling. Astronomers may need to rethink their own expectations, be ready for life and technology that looks totally different, or keep refining how and where they search. There's an important point here. Null results matter too. Not finding signs of civilizations tells us something about the distribution and rarity of high-tech life in the cosmos. It shapes future funding, public imagination, and the priorities of upcoming missions. Every new no narrows down the scenarios for what the galaxy is like. That's valuable knowledge, even if it feels a little disappointing compared to the idea of first contact. In the meantime, scientists are also looking for indirect signs. Large engineering projects might alter the brightness or spectra of stars. Civilizations might change their home planet's atmosphere in ways that are chemically odd. Even signs from the past, like the remnants of an extinct civilization, could show up in unusual patterns of minerals, isotopes, or modified environments. International teams working on these problems keep designing new algorithms and detection tools. Artificial intelligence and machine learning can sweep through exabytes of telescope data, looking for oddities no one thought to notice before. This includes weird star twinkling, erratic radio bursts, or light curves that don't fit standard models. As solar systems, exoplanets, and the spaces between stars all get mapped in more detail, it is turning out to be a complicated, fascinating, and sometimes humbling journey. The lack of clear signals or obvious neighbours does not prove we are alone, but it does mean the search is harder than just waiting for someone to phone home. The more we learn about planet diversity, migration, rings, moons, and the tricky business of habitability, the more background noise our galaxy gives us to sift through in the search for that one hello. For some, the great silence is a puzzle that makes them work even harder. For others, it's part of the mystery that keeps astronomy lively and challenging. Maybe answers are just beyond the current limits of what we can see. The exciting part is that as instruments get bigger and smarter, as surveys become all sky and global, and as humanity tries new and different ways to look and listen, the universe never stops granting new puzzles. Whether the silence is a temporary artifact of where we are in the search, or points to something profound about life's odds, each discovery about planets, stars, and phenomena out there sharpens the frame for whatever answer finally comes. Given how much effort goes into listening for distant civilizations and studying the huge variety of distant planets, it's no surprise that the future of exoplanet exploration is already one of the most dynamic areas in astronomy. The pace of technology and collaboration is speeding up as telescopes, satellites, and software tools become more powerful and flexible. Scientists are talking about a future where finding new exoplanets becomes so routine that the headlines shift toward what those worlds are like, how they evolve, and, even more importantly, whether any might hold signs of life. Right now, a lot of excitement revolves around telescopes that are just starting to deliver results, or will soon come online. The James Webb Space Telescope, for example, started its mission in the year 2022 and is already making a huge impact. This telescope does much more than simply look for new planets. Instead, it is built to analyze their atmospheres in fine detail, picking up fingerprints of molecules like water, methane, carbon dioxide, and other potential biosignatures. Because Webb works in the infrared, it can even detect the heat coming from distant planets, which helps when trying to measure their actual surface conditions and track any seasonal changes. Over the next few years, James Webb will continue to focus on the most exciting targets, like Earth-sized exoplanets in habitable zones around nearby stars, and provide the first ever detailed atmospheric readings beyond our solar system. Meanwhile, ground-based observatories are growing larger and more advanced. Telescopes like the Extremely Large Telescope in Chile, the 30-meter telescope being built in Hawaii, and the Giant Magellan Telescope are all set to deliver images and spectra at a resolution that was not even possible to imagine just a few decades ago. These massive instruments use adaptive optics that correct for the blurring from Earth's atmosphere, allowing them to spot planets that are smaller, closer to their stars, and farther away than ever before. They will be able to split starlight into incredibly precise spectra, letting astronomers hunt for both subtle chemical signatures and faint glimmers from entire new systems. Another important direction is direct imaging of exoplanets. This means blocking out the glare from a star to see the dim worlds right nearby. Special tools like coronagraphs and star shades are in development to make such imaging easier, and the ability to directly photograph more types of planets will keep pushing forward. Future missions, such as NASA's proposed HABEX and LUVOIR observatories, will take this to the next level by searching for true Earth twins around hundreds of nearby stars, studying their atmospheres, climates, and maybe even their surfaces. These observatories should have enough power to spot signs of oceans or continents by analyzing reflected light, or to spot cloud patterns and seasonal changes. A huge area of growth is the field of spectroscopy applied to exoplanet atmospheres, especially for smaller, rocky worlds that might be the best places for life. Already, space telescopes and instruments on the ground have found traces of water vapor, carbon monoxide, sodium, and even heavy metals in the atmospheres of hot Jupiters and sub-Neptunes. But the real ambition is to extend this to planets only a little bigger than Earth, especially in the habitable zones of red dwarfs and sun-like stars. When detailed spectra come in for the closest and most promising planets, scientists hope to finally be able to spot combinations of gases, such as oxygen and methane together, or unusual ratios of nitrogen, methane, and carbon dioxide that do not have easy non-biological explanations. The search for exomoons should also pick up speed thanks to better instruments and more creative data analysis. Larger telescopes can now watch for small shifts in a planet's motion or changes in brightness that might hint at the presence of a moon. It will soon be possible to confirm or rule out some of the candidates already found, and the first confirmed exomoon could lead to a rush of new discoveries. Moons, just like planets, may turn out to have their own atmospheres, weather, and maybe even subsurface oceans. The best tools will be able to study their size, composition, orbit, and how they affect the planets they orbit. Future work is not all about hardware. The rise of artificial intelligence and machine learning is making a big impact on exoplanet research. As data sets grow larger, sometimes to hundreds of terabytes from just one mission, AI systems are needed to pick out the faint but repeating signals of new planets, to reject false positives, and to spot unusual outliers that might escape a human's notice. These systems will get even better as they are trained on more examples, and new ways of automating the search and tracking the reliability of discoveries will mean less time spent on manual sifting and more on detailed science. Citizen science projects, where people around the world help classify signals and look for patterns, will also keep growing, blending human intuition with automated brute force. International collaboration is quickly becoming the new normal. The biggest telescopes and observatories are too expensive or ambitious for any single country to fund alone. Scientists from across the globe share time, money, and expertise. Data from missions like Kepler, TESS, Gaia, and James Webb are made openly available so that teams everywhere can look for new planets, check each other's work, and focus attention on the most interesting findings. Distributed networks of smaller telescopes, some run by universities or even dedicated amateurs, are used to follow up on candidates, refine measurements, and get faster confirmations. This collective approach is why research is advancing so quickly and why exoplanet discovery keeps breaking records year after year. Alongside the hunt for planets, there is renewed interest in looking for technosignatures, evidence of advanced technology, not just biology, on distant worlds. Scientists are coming up with new ideas about what sorts of signals to look for, from infrared patterns created by giant orbiting structures to pulsed laser beams, to global atmosphere changes that only industry or technology could explain. New arrays of radio telescopes like the Square Kilometre Array and upgrades to long-running SETI observatories will be able to scan the sky for faint, narrow-band signals from nearby stars or for unexplained bursts of energy. This approach is being mainstreamed alongside biosignature searches, adding a new layer of excitement to the search for life. Another area moving forward is the use of astrometry and gravitational microlensing to detect more distant or unusual planets. Gaia, the European Space Observatory launched in 2013, is able to measure the precise positions of over 1 billion stars. Changes in a star's position over time can reveal the gravitational tug of an orbiting planet, even ones that would never be found by transits or Doppler wobble. Combined with microlensing, where a passing star briefly magnifies a background star, sometimes revealing planets in the process, this will fill in gaps by adding worlds at much wider separations or at extreme distances from Earth. As the catalogue of known planets grows, so does the sophistication of the questions being asked. Rather than simply asking, "Is there a planet?" astronomers want to know how common solar systems like ours are, how often planets migrate or collide, how many systems have stable habitable zones, and how rare or normal Earth really is. Models can be tested by checking the overall population of planets, their sizes, distances from stars, and the chemistry of their host stars. The hope is to move from finding rare, easy-to-detect hot Jupiters and super-Earths toward a true census that includes Earth-sized planets at Earth-like distances, with real data about their atmospheres and orbits. On the habitability front, researchers are developing new ways to model the climates of entire planets or moons without ever visiting them. They simulate temperature, cloud cover, ocean currents, magnetic fields, and even biological cycles, then compare these models to data from telescopes. Using these models, it becomes possible to predict which planets are most likely to be comfortable for life and where biosignature gases or chemical imbalances might turn up first. This helps target the next wave of missions at the world's most likely to produce meaningful results. In the next decade or two, new missions designed specifically to find Earth-like planets and check them for life will come online. Europe's Plato mission, for instance, will launch in the late 2020s and will focus on finding rocky planets in the habitable zones of Sun-like stars. NASA and other agencies are planning satellites that will watch thousands of stars continuously, looking for the telltale signals of small planets passing in front of their host suns. Such missions, supported by even bigger and better ground observatories, should multiply the number of possible life-friendly planets and give teams the chance to follow up quickly on the most promising finds. Even as the tech improves, some aspects of exoplanet exploration will remain hard. Getting direct images of Earth-sized planets around sun-like stars is like trying to see a firefly next to a lighthouse from thousands of kilometers away. Tuning out the glare and interference and making sure you're really seeing a planet and not random noise or a background star takes painstaking attention. The same goes for teasing out faint traces of molecules in exoplanet atmospheres. False positives, signals from things other than planets or atmospheric features that have no connection to biology, are always a concern. That's why each major discovery gets checked from different directions by different teams and often with follow-up across years. The future also means more unexpected findings. As samples grow, so does the odds of seeing truly exotic systems, planets circling double or triple stars, worlds with wild seasons, rogue planets drifting between stars, and more. Unusual combinations, like rocky planets around massive blue stars or water worlds with thick, hazy atmospheres, will help astronomers figure out just how many paths to habitability are possible or how often life might start in strange places. All these missions, models, and searches for technosignatures or biosignatures are designed with the big questions in mind. Could there be life elsewhere, anywhere from bacteria to civilizations spread over multiple stars? Is Earth rare or one among billions of similar worlds? What new physics or chemistry is hiding in the atmospheres and orbits of strange planets? In the next 20 to 50 years, some of these questions may be answered. There's also a growing role for outreach and public participation. As space agencies make data public and citizen science platforms become more common, regular people can help hunt for planets, check suspected signals, and even propose new search strategies. Education programs and space missions now routinely include classroom resources, open datasets, and even ways for students to help interpret telescope images. This keeps excitement high and brings in fresh creativity and different perspectives. One more area to watch is the development of low-cost distributed networks of smaller instruments. Not every planet will be found by a billion-dollar telescope. Some of the most interesting discoveries, like the transit of Proxima Centauri b, came from a mix of large and small observatories. Networks of moderate telescopes in different countries can provide non-stop monitoring, rapid follow-up of transits, and more eyes on potential signals of interest. Increasingly, exoplanet discovery is a team effort spread across continents and time zones, where big science and small science work together. Finally, the coming decades of exoplanet discovery will almost certainly include surprises. New techniques, oddball transit signals, funny atmospheric mixes, or signals that just don't fit known categories are inevitable as the catalogues keep growing. The challenge won't just be finding more worlds, but figuring out their origins, their potential for life, and their histories. What started out less than 30 years ago with just a handful of known exoplanets has already become one of the fastest moving frontiers in astronomy. No matter what new data comes in, Earth remains the place where the questions started, but it's no longer the only point of reference. With every new telescope, instrument, and set of curious eyes, the inventory of planets grows richer and more varied. The road ahead involves digging into that diversity, looking for the patterns and exceptions, and narrowing down what we know about how planets form, evolve, and maybe support life. Whether or not we find alien civilizations or oceans teeming with life on distant moons, the next era of exoplanet exploration will totally reshape humanity's sense of the universe and our place within it.